Hi, this is Dane Quinn from the University of Akron, and today I would like to do an example dealing with planar kinematics. We have a block, shown here, that slides to the right with speed v, while the bar, which has length L, is pinned to the block at the center of the block, point C, and rotates with angular speed omega. And the rotation here is clockwise. I'd like to find the velocity of the point A, which is at the end of the bar. So, looking at this, we need to start off and define coordinates and directions. So, the directions we'll use will be I and J, fixed in the ground, horizontal and vertical, which is along the surface and perpendicular. And then, in addition, we'll define directions E1 and E2 as fixed in the bar. So as the bar rotates, these directions rotate with the bar. Then we can identify coordinates x, which is the displacement of the block to the right, and then theta, which is the rotation of the bar. So here the directions E1 and E2 are oriented with respect to I and J by the angle theta. So now, if we want to relate E1 and E2 to I and J, we can do that. Here E1 is cosine of theta in the I direction plus sine of theta in the J direction, while E2 is minus sine of theta in the I direction plus cosine of theta in the J direction. And we can also relate I and J back to E1 and E2. Here I is cosine in the E1 direction minus sine of theta in the E2 direction, and J is equal to sine of theta in the E1 direction plus cosine of theta in the E2 direction. And you might want to pause this video solution right now and work through these coordinate transformations. So now, with that, the velocity of the block can be written in terms of I and J and the coordinate x, so that v of c, c here is the point at the center of the block, is equal to x dot in the I direction. In addition, we're told that the bar, b, rotates clockwise with angular speed omega. So here, the angular velocity of the bar can be written in terms of theta as theta dot in the k direction. Now, because the block slides to the right with speed v, the velocity is v in the I direction. Now, the bar, which rotates clockwise, is minus omega in the k direction. So with this, theta dot can be seen to be minus omega, and x dot is equal to v. Again, the block is assumed to move to the right with speed v, so that's v in the I direction, and the clockwise rotation of the bar implies that the angular velocity is in the minus k direction, and the speed is given as omega. Looking at the figure and the system again, we see that both A and C are fixed in the bar. So we can relate those two velocities. Again, because they're fixed in this frame of reference that's attached to the bar. So as a result, the velocity of A is equal to the velocity of C plus the angular velocity of the bar cross the position of A with respect to C. So now, from the problem statement and the way that we've defined the coordinates, we see that the position of A with respect to C, it's going to be this vector, is minus L, L is the length of the bar, in the E2 direction. So here, recall that the velocity of C was v in the I direction, the angular velocity of the bar was minus omega in the k direction, and the position of A with respect to C is minus L in the E2 direction. And therefore, we can solve for the velocity of A. Velocity of A is v in the I direction, plus now the angular velocity, which is minus omega k, cross minus L E2. And I do want to point out that this is the angular velocity of the bar, given as omega the bar, and it's a vector, while in this representation, omega is the angular speed. I realize they have the same sort of symbol, Greek letter omega, but this one's a vector and this one's a scalar, so they're actually two different things. They're closely related, obviously, but there is a subtle difference between the angular speed and the angular velocity. So now, evaluating this cross product, we find that the velocity of A is v in the I direction minus L omega in the E1 direction, because k cross E2 is minus E1. And we have these other two minus signs that cancel out. We can attribute these two terms to two different sources. In particular, this first term, v in the I direction, is due to the motion of the block. Right, so the block slides to the right with speed v. While this second term is due to the rotation of the bar, namely clockwise with angular speed omega. And they combine to give us the overall velocity of A at the center of the bar. Now, notice that I have used the I direction and the E1 direction for these two terms. If I would like to express this in a consistent set of directions, I can either take I and express it in terms of E1 and E2, or E1 and express it in terms of I and J, and we'll do the latter. Right, so recall that E1 is cosine theta I plus sine theta J. So finally, the velocity is v minus L omega cosine of theta in the I direction, plus, now in the J direction, minus L omega sine of theta in the J direction. So again, we can write this in a consistent set of directions, and the velocity of the end of the bar depends not only on v and omega, but the position of the bar as well. So that's it for this problem. It's relatively simple, but it's a nice introduction to planar kinematics. Thank you.